She's like, oh, this is boring. Boring, Dad. Okay, so today we have maximum and minimum values, finding maxes and mins. And the first thing we start off with are local extrema. So that is just a fancy word for maximums and minimums. So number one is talking about a local maximum. This is what happens when your graph goes from rising to falling. So that is the graph below. So if we have a graph that rises and falls, you create a local high point, which is called a local maximum. And this will happen at some value of C on an interval AB. So to make it easier, this value of C will be called a critical number. And at critical numbers, we can find maximums or minimums. Okay. And then number two talks about a local minimum. So if the graph goes from falling to rising, then a low point is created. And that low point is considered your local minimum. And again, this happens at a value of C. Okay. 3, the value f of C is called a local extremum if it either has a local max or local minimum. And wherever a local max or minimum occurs, that is also considered a turning point. Remember, turning points is where the graph changes direction. The graph goes from falling to rising or rising to falling. So that's what a turning point is. Okay, so those are the definitions of local maximums and local minimums. All right. And then we have the definitions of absolute maximums and absolute minimums. So if you have an absolute maximum, it is the absolute highest point on your graph. And this will also happen at that value of C, that critical value. So the graph in the middle shows what an absolute maximum is. This point of 0,4 is the absolute largest or highest point on the graph and is considered the absolute maximum. And then an absolute minimum, of course, the opposite. It is the absolutely lowest point on the graph, which is shown in graph 3. It is the absolute lowest point. Okay, graph 1 shows no absolute max or mins. The first graph shows only local maximums and minimums. So this point would be a local max. This point would be a local minimum. There are no absolute maxes or mins because you see that these tails head towards infinity and negative infinity. Okay, so those are definitions of absolute maximums and minimums. Okay, and there's a nice little theory that goes with absolute maximums and minimums. It says if you have a closed interval, then on this closed interval, you will have an absolute maximum and you will have an absolute minimum at the critical numbers C and D of our function. So the graphs below just show graphs with closed intervals. So the first one has a closed interval from 2 to 12. And on this closed interval, the function has an absolute minimum at 24 and an absolute max at 154. And then if you change up the closed interval on the same function, well, you change up the absolute max and minimum. On this interval, we made it 410. So once you change up the closed interval, the max is now at 105 and the absolute minimum is at 73. Okay, and again, change up the interval, 4 to 8. The absolute maximum stays 105, but the absolute minimum changes to 78. And then on the fourth one, change the interval to 3 and 11. Well, the absolute maximum, you now have 2, and they both occur at 105, of course, with different x values. And then your absolute minimum is at 73. So what this is saying is that on a closed interval, whether you have a closed interval or not, you can have multiple absolute maximums or absolute minimums. And that also goes for local maximums and local minimums. Okay. All right. Next is Fermat's theorem. If f has a local maximum or minimum at some number c, and if the derivative exists at this value c, then the derivative at this value is 0. So what that means is what I said when we started the notes, is that to find maximums or minimums, we're going to take the derivative and we're going to set it equal to 0 and solve for values of x. Well, if the derivative exists and we find those values, well, it only makes sense that if you plug them into the derivative, they would zero out the derivative. Because again, the process is you take the derivative, set it equal to 0, and solve for x. Okay. And another definition, a critical number of a function f is a number c in the domain of f such that the derivative will equal 0 or the derivative does not exist. So again, that's just an extension of Fermat's theorem. What is wrong, little fussy girl? Sorry, she's here. Yay. No nap, no nap. All right. So if you find a critical number, you can find a maximum or minimum at it. All right. And Ryan, floor is yours. Let me see if I can hand this baby off.
Oh, I have to log in my character.
Oh my goodness.
Account.
All right. Well, I'll be back.
All right. Yeah, it'll be just a sec.
So fussy. Okay, never mind. I beat him. Ha! All right.
God dang it.
You can do another one.
That was your chance, Ryan, to shine.
I already shown before doing that related rates.
Okay. So what we're going to do is we're going to take this function and find the critical numbers. All we're going to do is just practice finding the critical numbers. That's it. So again, to find critical numbers, you're going to take the derivative, set it equal to 0, and solve for x. Okay. So let's start with number 1. And I'll rewrite this. F of x equals x to the 3/5 times 4 minus x. And then you can use product rule on this, but it's probably going to be way easier just to distribute it and then take the derivative. So let's go ahead and distribute that, and you'll get 4x to the 3/5 minus x, and x to the 3/5 times x should give me x to the what?
The 8/5.
Good. X to the 8/5. There we go. Now take the derivative, and we're going to get 4 times 3/5. What's that? 12/5. 12/5 x, you take 1 away. That's going to be to the negative 2/5 minus 8/5 times x. And you take 1 away, and you get 3/5. Okay. So there's our derivative. Now to find the critical numbers, you set the derivative equal to 0. Okay. So we have 12/5 x to the negative 2/5 minus 8/5 x to the 3/5 equal to 0. Ooh, looks great. So we want to solve for x here. So let's go ahead and simplify a bit. What could I factor out from this equation?
4/5 to the -2/5.
Good. So we're going to take out 4/5 x to the negative 2/5. All right. And if I take out 4/5 x to the negative 2/5, what does that leave me with inside?
3 minus 2x.
3 minus just 2x. Very nice. Okay. So you factor out 4/5 x to the negative 2/5 over 3 minus 2x. Next, I'm just going to rewrite this as a fraction. I'm going to put this as 4 times 3 minus 2x over 5x to the positive 2/5. Okay. So for this one, to find critical numbers, if you're given a rational equation, then critical numbers will come from the numerator and critical numbers will come from the denominator. So let's look at the critical numbers from the numerator. All we're going to do here is just set 3 minus 2x equal to 0. And we're going to solve for x. So 3 equals 2x. And our first critical number is 3/2. Okay. And then you're going to set the denominator equal to 0. So 5x to the 2/5 equal to 0. Don't need that 5. So you get x to the 2/5 equal to 0. And even if you get rid of this power, x is still going to equal
0.
0. Good. All right. And these are the x values found from the first derivative. So these x values are going to be considered our critical numbers. Okay. And of course, this example, we just wanted to find critical numbers. We didn't want to do anything else, but we know that at these critical numbers, a maximum or minimum will exist. Okay. I guess one thing to take note of, let's see. 0, let's see, for the derivative, 0, you can't plug in 0, but 0 would work in the original function. So that's something to think about. Okay. Any questions on number 1? All right. Everybody good?
You're good.
Okay. All right. Next example. This is called the closed interval method. So we saw on that second page of definitions, if we have a closed interval, then we are going to be able to find absolute maximums and absolute minimums. So we're going to be given a closed interval. And then what we're going to do next is find the derivative, set it equal to 0, and solve for x. After we get those critical numbers, we are going to see if they fit in our interval and then test them in the original function to find absolute maximums or minimums. Ugh. But again, I'll walk you through it. Okay. So example 2, we're going to find the absolute maxes and mins. So our first step is find the derivative. So I'll just say step A, we take the derivative and we get 3x squared minus 6x. And then your next step is set the derivative equal to 0. Okay. So in this one, you can factor out 3x, and this will leave us with x minus 2 equal to 0. Okay. So what are my two critical numbers?
0 and 2.
Good. 0 and 2. These are my critical numbers. Okay. And what we want to do next is test the endpoints and the critical numbers into the original function. But what we want to know is, do these critical numbers fit in this interval?
Yes.
Yeah, this interval is from -1/2 to 4. So do 0 and 2 fit in there?
Yes.
Yes. Good. So step C, we are going to test our critical numbers and endpoints. Okay. And if the critical numbers did not fit in the interval, then you would just discard them. That's it. So I'll make a lovely little XY chart here. And I'll put our X values in order. My first endpoint is at -1/2. So I'll put -1/2 here. And then my critical number is 0, 2, and then my last part of the endpoint is 4. We don't need any other X values because on a closed interval, an absolute maximum or minimum may occur at the endpoints or at critical numbers. So we don't need any other numbers in between these. Okay.
So if the numbers were outside of the interval, does that mean that the maximum and minimums would be the ranges? Or would be the first and last number?
Yeah. So let's say if these two didn't fit, then the absolute maximum and minimums would occur at those two.
Okay.
Yeah. Good. Okay. And you will plug into the original function. So we're going to plug them into x cubed minus 3x squared plus 1. All right. So Desmos, why not? Hide video, hide that, and bam, I'll type this in. x cubed minus 3x squared plus 1. And then I'll do the table feature, cheat codes, and I get negative 0.5, 0, 2, 4. And then negative 0.5, 0.125, 0, we get 1, 2, we get negative 3, and 4, we get 17. Okay. And all we're doing here is finding the absolute max and absolute minimum. So which y value is the largest?
The 17.
17. So this would be considered the absolute max. And which y value is the smallest?
93.
Negative 3. So this would be considered an absolute minimum. Okay. And that's all you do. And it looks like, based on our values, we have an absolute min at one of our critical points, and we have an absolute max at an endpoint. Okay. So any questions on that process? Everybody's good? All right. Oh man, how many problems? Let's see. That's good. All right. You want to get in on any of these, Ryan?
I knew you were gonna have me do this one. All right, yeah, I'll do it.
Cool. Cool, man. This
Okay.
one's not bad. All right.
Mm-hmm.
Mm-hmm.
So our first step is to
not-
find.
You're not sharing your screen.
Oh
Share your screen.
Don't tell me. Don't tell me that now.
I have a quick question, and
What's that?
I'm sorry because I was a little bit late. So the critical numbers, if we were to plug those back into the original equation, that would give us our absolute minimum and maximum, or am I confusing things?
So if you take the critical numbers and plug them into the original function that's not on a closed interval,
Mm-hmm.
then that would give you a local max or a local minimum.
A local, okay.
Good question.
Any more interruptions? No, I'm just kidding.
Hey, at least you're earning your money today, all right?
I earn my money every day. Every day. All right, so our first step is to find g prime of x. So to find g prime of x, we're gonna have to, do you guys prefer product rule or quotient rule?
Quotient.
Surprise me.
I
Surprise
was
you.
gonna go surprise also.
Just pick one. We'll do, all right, we'll do quotient rule. Why not? So that means that f is gonna be my numerator, g is my denominator. So f prime will be 1, g prime will be 2x minus 1. So now following the quotient rule, we have f prime times g. So that's just going to be x squared minus x plus 1 minus g prime times f. So I'm going to set up parentheses. So we have g prime, which is 2x minus 1 times x minus 1, all divided by the denominator squared. Squared. Now we just clean this up a bit. So if my first set of terms aren't going to change, so we have x squared minus x plus 1 minus, and then I'm going to distribute these two factors. So we're going to have 2x squared minus 2x minus x plus 1, all divided by, and then x squared minus x plus 1. So now distributing that negative sign, again, my first set of terms do not change. We'll have negative 2x squared, and then negative 2x minus x is a negative 3x, and then times a negative 1 will be a positive 3x. And then lastly, 1 times negative 1 is negative 1. Now I just look to combine like terms. So I have an x squared and a negative 2x squared. So that's just going to give me a negative x squared. I also have a negative x and a positive 3x. So it's going to be a positive 2x. And then lastly, we have 1 minus 1, which is 0, all over our denominator, x squared minus x plus 1 squared. So there's our derivative. Now I set g prime of x equal to 0, which means we have negative x squared plus 2x over x squared minus x plus 1 squared. And set that equal to 0. And now we can start looking for our critical numbers. So my critical numbers come from solving my numerator by setting that equal to 0, as well as the domain restriction of my original function. In this case, the domain restriction will come from my denominator. So again, my first critical numbers be coming from solving my numerator by setting it equal to 0. And I see that I have a common factor of x. And we'll just factor out a negative x just to make my leading term positive. So we have positive x minus 2 is equal to 0. This means my solutions will be x equals 0 and x equals positive 2. So far, so good.
Yeah.
Sweet. See
Gotta
one
look
thumbs
for
up.
those. Yeah, so you got to look for the thumbs up.
All right, so next is that I have to set my domain restriction. So looking at my denominator, I'm going to set x squared minus x plus 1 equal to 0. And this is where another set of critical numbers can come from. So we have a quadratic set equal to 0. So my way of solving this would be to factor. But is this factorable? I'll give you guys a hint of how to tell if something's factorable. What are two numbers that multiply together that give us 1, that when added, give us a negative 1?
I don't think they, wait, no.
Nothing, right? There's nothing that multiplies together to give us a -1 when that multiply together to give us a +1 that when added together give us a -1. So this does not factor. So what's another way of solving a quadratic that is set equal to 0?
Quadratic formula.
The quadratic formula. So we have the quadratic formula says that x is equal to -b plus or
How
minus.
Dare you?
You want me to complete the square on this?
Yeah, I want you to complete the square.
I want to show him a trick about this to save him time though.
Fine, fine. I knew this would happen.
Did anybody else learn a song to memorize this?
I sure
Yes.
did.
Okay, I was just making sure because I was totally singing it.
You need to create
So-
a catchier song for completing the square.
Let's hear it.
I'll get on that over the weekend.
So kind of to go back what we were talking about, right? We're looking for critical numbers that exist on a real number coordinate system, right? Meaning that our solutions cannot be complex numbers. So the trick is, to save you guys a lot of time, is actually to look at what's called the determinant. These set of terms within the square root will tell you whether or not these solutions will be complex or real numbers. Meaning, if I solve the determinant and get a negative number, I can stop there. Because again, that will tell me that the solutions for x will have to be complex, which means there are no real numbers for x that would cause the denominator to be 0. Does that make sense?
It seems
Looking
more
for-
complicated than completing the square.
Okay. So b squared is -1 squared, right? -4ac will be -4 times a will be 1, c will be 1, and this will be a -4. This will be a 1. Is 1 minus 4 a negative number?
Yes.
Yes.
It is a negative number, meaning I can stop, right? This is a negative solution. Meaning the determinant is negative, meaning there are no values of x, real numbers that will have x squared minus x plus 1 equal to 0. So there are no critical numbers that come from this.
So I have a question then. How
Sure.
come when we set the original the equation that we got and we set it to 0, how come we didn't just divide by that on both sides and then it would be gone?
Because you're eliminating potential solutions.
But there aren't any critical numbers from it.
Well, I mean,
But
if you
you-
divide it out, you eliminate any possibilities of there being any critical numbers,
Okay.
right?
Yes.
Are you saying like take the denominator and move it to the right to become 0?
No, multiply it by 0.
Okay, yeah, because
I'm still trying to understand this.
no, yeah, because when you're dealing with critical numbers, you don't want to get rid of any x values.
Okay.
So you want to go through this process that Ryan is showing to see if the denominator has critical numbers, because that's what we did for the first example. If you end up with a rational equation, no matter what, you want to set the denominator equal to 0.
Okay. So we're just setting it equal to 0. We're not solving for it. I think that's where I'm hung up on.
So you're
Well-
looking for an asymptote. So the idea is that you're trying to determine the behavior of this function by identifying maxes and mins. Problem is that if you don't identify asymptotes, you may assume that there's a point on the function that is a maximum when in fact it's an asymptote. So say for instance, you have a function that looks like this. We'll do 1 over x, right? So there's our asymptote. And there's our function, right? If we're evaluating to the right of this asymptote, you would assume that this is decreasing, right? And this is decreasing to the left. So when you look at this, if you're just looking at it on a number line, without realizing there's an asymptote, you could be kind of confused as to what this function is doing, right? Because it looks as though that it's decreasing on both sides of a critical point, which it shouldn't happen if it's a critical point, right? It either increases and decreases on one side, or it decreases and then increases. In this case, they're both decreasing. So by solving these denominators and identifying these asymptotes, you're able to see what this function is doing a little more clearly than you would if you just ignored these asymptotes.
I think I just wanted to confirm that we weren't solving for 0. We were just setting it equal to 0, but thank you. For some reason, I thought we were solving for it. But
You're
it's-
looking for values of x that would cause this equation to be true, right?
Mhm.
Right. So if I plug a number in for x, this left-hand side should become 0. The question is what number for x would cause that left-hand side to be 0? And there are no real numbers, right? That's what these steps showed us.
Okay, thank you.
Yeah. Cool.
All right, so this, instead of having to like try to find all these critical numbers from solving the denominator, I saved myself some time by just looking at the determinant, right? And I saw that the determinant was negative, meaning there are no critical numbers that come from the denominator of my rational function. So my only critical numbers are going to be x equals 0 and x equals 2. So then my critical number 0 and 2. Do we have an interval? We
Oh
do
no,
not.
I think that one just said, I think you're done because it said find the critical number.
Oh, that's it. Okay.
Yeah, that's it. Yeah.
Then we're
That other
good.
part I think is for next class. The whole sign chart thing.
Gotcha.
Yeah.
And we're all set.
You want next one or no? I mean, I'll do
So
it.
can you, like without doing the quadratic, I guess just show us like quick, what if you completed the square, what would happen?
Sure.
Yeah. Good. 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 Good.
And I'll show you that quadratic actually would have been quicker.
No.
Just for our purpose,
The
not for
quad-
actually
the quad-
solving this.
The quadratic, we get 1 ± 3i/2, right?
Right, but
Yeah.
all that's not a. So remember that we're looking for real numbers, right? And those
Yeah.
solutions are complex,
Yeah, I got that.
meaning we have no use for them, which is why I only did this shortcut. All I care about is whether or not my solutions would be complex. All right, so now we're gonna do completing the square, right? So completing the square, do you guys do it by moving your constant to one side, or do you prefer doing it just leaving all your terms
Move the one
equal to
over.
0?
Move the
Move
one
the
over.
Okay,
Yeah.
so we have x squared minus x is equal to -1. So to complete the square, you divide the middle term's coefficient, which is an understood -1, by 2, right? So b over 2 is equal to -1/2. You then take that value and square it. And what's -1/2 squared? One half? No,
1/4.
I'm just kidding. 1/4, right? Now we add that to both sides of our equation. So we have x squared minus x plus 1/4 is equal to -1 plus 1/4. I don't know if you guys can see that, but
Yeah, you're good.
whenever you complete the square, the perfect square is x plus your b over 2, in this case, minus 1/2 squared. And that is equal to, and then -1 plus 1/4 is a -3/4. And then what would your next step be to solve this equation? It would be to square root both sides, right? But what happens if I square root the right-hand side of my equation?
Get a complex number.
Right, so you can stop here. This is a complex solution. Ooh, what is that? So no critical numbers. Did that make sense?
Yes.
Woohoo. All right, good. I'll do it.
Doesn't matter to me. Go for it. We'll alternate. How's that?
Sounds wonderful. Oh, wrong screen. There we go.
Oh no, I didn't see this next one.
This is a natural log. I don't know if it's as bad as this one. This one's not bad though. Remember your identities. Okay, so all we're doing is finding critical numbers, and whatever we find needs to be inside this interval 0 to 2 pi, which is the unit circle. So let's do it. All right. Oh yeah, before we do that, let me rewrite this as f of theta equals 2 cosine theta plus, and I'm going to rewrite this as sine theta to the second power. Okay, just so we can see the chain rule going on. So we take the derivative and you get -2 sine theta plus 2 sine theta times cosine theta. Perfect. Okay. So there's the derivative. And now after you take the derivative, we set it equal to 0. So we get -2 sine theta plus 2 sine theta cosine theta equal to 0. And now let's solve for theta. So what could I factor out here?
Added 2 sine theta.
Take out a -2 sine theta, and what does that leave me with?
1 minus cosine theta.
1 minus cosine theta equal to 0. And then set both of these equal to 0. Okay. And first up is sine theta equal to 0. And next is cosine equal to 1, or 1 equals cosine theta. Okay. And now on your unit circle, what values of theta make sine 0?
Two pi and pi.
What else? So
And
full Good, because it's a full
Pi.
revolution. So 0, pi, 2 pi. And then what makes cosine equal to 1?
0 and 2 pi.
0 and 2 pi. Perfect. These are our critical numbers. Okay, but then what if these restrictions weren't here? You would have to make a formula, a general formula solution to represent infinitely many answers. So how would you represent all of the radian values that make sine equal to 0? It looks like it happens at every what?
Every pi.
Every pi. So our general solution, we could just say pi n or pi k, right? How would you represent it for cosine?
Theta equals 2 pi.
Theta equals 2 pi n. Would that represent every even one? Yes? No? Maybe?
I thumbs up it, yes.
Oh, I think I closed that. All right. Okay, cool. So there's that. All right. Any questions on that one?
No.
All right. Ooh la la. I got it. It's fine.
Say what?
So I got it.
Oh, I'll see how it is.
Yeah, yeah, yeah,
Yeah, yeah, yeah.
yeah. All
Yeah,
right.
yeah. I was getting ready.
Well, we'll give you another one. Don't worry. There's another trig one around there somewhere. All right. F of x equals x to the negative 2 times the natural log of x. So again, we're just finding critical numbers. So here we're going to do product rule, right? F is x to the negative 2. G is the natural log of x. F prime is negative 2x to negative 3. G prime is 1 over x. Okay, so the derivative f prime of x, f prime g, negative 2x to the negative 3 times the natural log of x plus g prime f, 1 over x times x to the negative 2. Okay, so there's our derivative. Let's make it look pretty. This is negative 2x to the negative 3 natural log of x. And what is 1 over x times x to the negative 2 going to be?
1 over x cubed.
1 over x cubed, or even better, x to the negative 3, right? Okay, so now set this equal to 0. And what could we factor out?
X to the negative cube.
Good. X to negative 3 leaves me with negative 2 natural log x plus 1. Okay. One more rewrite, because now we have what type of equation? You got your rational, right? So we'll look at the numerator first. Our numerator, negative 2 natural log x plus 1, set it equal to 0. Okay. Move the 1 over. Negative 2 natural log x equals negative 1. And then the natural log of x equals 1/2. So how do we get that x out of the argument of the natural log? What do we convert to?
Exponential.
Exponential. What's the base of the natural log?
E.
E. So what's our answer for x?
E to the
X.
E to the 1/2?
yeah.
Okay. And then the easy one, the denominator. X cubed equals 0. Therefore, x is
3.
yeah. Okay. Here's where we have to be careful though, right? Because whenever we're finding max or mins, we have to take these critical numbers and plug them into the original function. So when we find critical numbers, we want to make sure the numbers we find fit in the domain of the original function. So if I were to plug this in into the original one, what would the outcome be? And I'll even rewrite it as this. Natural log of 0 over 0 squared. What is the natural log of 0?
Is it undefined?
It's undefined. And the other thing that offsets this is, can you have a 0 in the denominator?
No.
No. So this becomes undefined, which means that x equals 0 is not a critical number. So our only critical number here is e to the 1/2. Yeah. Any questions on that one?
For these kind of problems, we're not going to have where they're both undefined, right? Like to prove it's a real function,
For
where they mean we're finding critical numbers.
mhm.
Yeah.
So if they both happen to be undefined, then that's something that may happen.
Okay.
Yeah. Because let's say we were given a function. What's a good one? I guess you could say like 3x cubed plus, I don't know, let's say, because that'll be squared. And then let's just say like 9x or something like that, right? Well, if you took the derivative, you'd get 9x squared plus 9. And then you could take that 9 out and have x squared plus 1. Can you factor x squared plus 1?
No. Because
No,
you tried to take the square root of a -1.
exactly. So you'd get x equals plus or minus I, which cannot be considered critical numbers. So we would just say, if you got a problem like that, your critical numbers do not exist. So there could be an actual problem where you don't have any critical numbers at all.
Okay.
Okay. Cool. All right. All right, you're up. Tag in, Ryan.
Put me in, coach.
Gotcha. Bam.
Boom. Oh, wait, that's the wrong one. There we go. All right, so find the absolute max and min values of f on the given intervals. Okay. So if we're looking for maxes and mins, we need to take the derivative of the function. So f prime of x will be the derivative of the first term, which is 6x squared, minus the derivative of the second term, 6x, minus the derivative of our third term, 12, and then the derivative of any constant would be 0. Next is we take our derivative, set it equal to 0. Means we have 6x squared minus 6x minus 12 equal to 0. I have a common factor of 6. So we have 6 times x squared minus x minus 2 is equal to 0. So far, so good. Yeah, sweet.
Look for the thumbs up. I got my screen back up. You got a thumbs up.
I got a thumbs up, sweet.
Yeah.
All right. So now we're going to set x squared minus x minus 2 equal to 0. Because again, if I just divide 6 to both sides, we'll be left with x squared minus x minus 2 is equal to 0. Now we get to try and factoring this. So by factoring this, I'm looking for two numbers that when multiplied together, give me a -2. And when they're added together, give me a -1.
-2 and +1.
Good. Now I can set each of my factors set equal to 0 separately. And then we'll have the solutions x equals 2 and -1, or -1 and 2. But remember, we were given a closed interval, right? So we need to make sure that our critical numbers are within our interval. Are the numbers -1 and 2 within the interval from -2 to 3?
Yes.
Yes.
They are. So these are our critical numbers. So crit numbers. So next is that it's asking us to find the max and min values of this given function within this interval. So to find the max and min numbers, all you have to do is take your critical numbers and your endpoints and plug them into the original function. So we have our XY chart. And then plugging in order, we have -2, -1, 2, and 3. And then pulling out your handy calculators. X squared minus 12x plus 1. All right. At -2, we have a -3. -1, we have 8. At 2, we have a -19. And then at 3, we have a -8. So where would our absolute maximum be?
-1, 8.
Good. So our absolute maximum will be at -1, 8. And our absolute minimum would be where?
-19.
Good. That's it.
Yeehaw. Good fun.
We did it.
All right, you want next one or you want trig?
Ooh. Can I show him a trick on this one?
Sure. You got it.
Sweet. Okay. So in this case, are they asking us to find the absolute maxes and mins like on the
Yeah,
previous one?
it's still
Okay.
absolute maximums. Yeah.
Okay. So do you guys want to do this using product rule or an easier way?
Are we allowed to use the easier way on the test?
As long as you're
Yeah.
good with your algebra.
If we're showing it here, then yes.
All right.
So they're
Okay.
down.
So I'm going to rewrite this function real quick. What I'm going to do is I'm going to force this x inside of the square root. But in order
Savage.
for me to force that x into the square root, I have to square it, don't I? So that leading x will become x squared, but inside the square root. Like that. Does that make sense?
Yeah, we've totally done this before.
Okay. So now I no longer have a product rule. Instead, I can distribute this x squared inside these sets of parentheses, and instead just have a chain rule. So distributing that x squared, we have 4x squared minus x to the 4th. So far, so good. Thumbs up, sweet. So now finding f prime of x using chain rule. Well, remember that this square root is the same as the 1/2 power. So applying power rule to that 1/2, we'll have 1/2 times that. So again, brought down the exponent, kept the inside function the same, subtracted 1 from the exponent. Now I multiply that by the derivative of the inside function. The inside function is just 4x squared minus x to the 4th. So that derivative will be 8x minus 4x. Do you hear Skip just like coughing? Shut up, bud. Okay. So there's our derivative of the inside function. So now I got to clean this up because remember we have to set this equal to 0 and solve. So I know this negative exponent tells me to reciprocate the base of that exponent. So I'm going to pull that 4x squared minus x to the 4th down to the denominator. So we have 8x minus 4x cubed over 4x squared minus x to the 4th to the 1/2. And then just making it one fraction, we have 8x minus 4x cubed all over 2 times 4x squared minus x to the 4th to the 1/2. And looking at our numerator, do you guys see that they both have even coefficients, right? Meaning I could factor a 2 and reduce with a 2 in the denominator. So this will reduce to a 4. This will reduce to a 2. So now we have 4x minus 2x cubed over 4x squared minus x to the 4th to the 1/2. So far, so good.
Doing good.
Sweet, sweet. Now we take our derivative, set it equal to 0. That means we have 4x minus 2x cubed over 4x squared minus x to the 4th to the 1/2. And that is equal to 0. So again, our critical numbers can come from both our numerator as well as our denominator. So for our numerator, we have 4x minus 2x cubed is equal to 0. Factoring this, I see we have a common factor of, so I see that my leading term would be the highest power, right? So my leading term is a negative 2x cubed. I'm going to make that positive by factoring out a negative 2 from both terms. And then both terms have a common factor of x. So now my leading term will be x squared minus 2. So far, so good?
Yep.
Sweet. Now that I have this in factored form, my first factor will be negative 2x equals 0, which means that x would be 0. My second factor would be x squared minus 2 equals 0. Solving for x squared, we'll have x squared is equal to 2. And then square rooting both sides, we'll have what? X is equal to
Square root of 2.
just square root of 2.
Plus or minus the square root.
There you go. Plus or minus the square root of 2. So now we have our numerator solved. Now we solve our denominator. So setting my denominator equal to 0. Actually, don't need the radical. We'll just set the inside of the radical equal to 0. Squared minus x to the 4th is equal to 0. So now factoring this, again, I see my leading term, which is negative x to the 4th. I want that to be positive. So I'm going to start by factoring out a negative. And then both terms have a common factor of x squared. So now we'll be left with x squared minus 4 is equal to 0. Now we have negative x squared is equal to 0. So we get x is equal to 0. Our second set of solutions, well, we'll have, if you guys can see this or not, tell me, x squared minus 4 is equal to 0. And this is a difference of squares. So we have x plus 2, x minus 2 is equal to 0. So x equals negative 2 and 2. So far, so good. Sweet. Now we got to kind of look over our critical numbers, right? So our first critical numbers for both solutions is x equals 0. But can that be a solution? Meaning, can I plug that into my function and it give me an output? What happens if I plug 0 into my denominator?
It becomes undefined.
Becomes undefined, right? That means that x equals 0 cannot be a critical number.
Wait. No, it has to be into the original function.
Oh, wait. Did I do my derivative? I sure did.
Yeah, you
Oh,
plugged it
never
into
mind.
your
I'm
derivative.
sorry about that. Sorry, guys. My bad.
I think it works in the original, right?
Yeah, it does.
Maybe.
It'd just be 0.
Yeah.
Okay. Sorry about that. So now we got to test, make sure our solutions are within our interval. So going back to our interval is from -1 to 2. So I'll write that here. Interval is from -1 to 2. So is 0 within our interval?
Yes.
Sure is. Is plus and minus square root of 2 within our interval? Sure is.
What's that? 1.4? I don't know.
Yeah.
Yeah.
I think it's something like that. So 1 point.
Yeah. 1.41.
So one of them is not. So positive
is.
square root of 2 works. Negative square root of 2 does not work. And we've already checked 0. And then our last ones, we have -2, that is outside of our interval. +2 is within our interval. So now we get to write our XY chart. I'll do it over here. So we have our X, our Y, because now we need to find our absolute maxes and mins. So writing our endpoints and our critical numbers, we have -1, we have 0, we have the square root of 2, and we have 2. Pulling out our handy dandy calculators. We're going to plug this into our original function. So we have x times the square root of 4 minus x squared. Okay, so plugging in -1. Oh, what is that? Goodness. I have negative 1.732. Plugging in 0, we have a 0. Plugging in the square root of 2, we get 2. And then plugging in 2, we get 0. So in this case, our absolute maximum will be what?
Square root of 2, 2.
Right. Thought I heard someone else, but they were super quiet.
Yeah, it was super low.
Was I really low?
Yeah, yeah.
Yeah, Amanda just stole your thunder. It's all good.
I did.
I'm sorry.
It's okay.
And then your absolute minimums would be what?
I got this. I got this. Negative 1, negative 1.78 or 32. What did I get?
So what is it?
Negative 1 and negative 1.732.
Right. Boom.
Nice.
We did
All
it.
right. Woo. All right. Woo. Here we go.
Have fun, Trig
Yeah,
Master.
man. 20 minutes to knock this out. Got it.
20 minutes. What? Shouldn't take you 20.
No, it won't. Or will it?
How are you guys doing today? So who's seen Kong versus Godzilla?
I saw it.
You what?
I saw it. On my
We're
HBO
over.
on my
We're
HBO
over.
Max account.
You mean mine?
Yeah. Nice. All right. Cool. All right, let's do it again. One last time. Hoo, hoo, hoo. All right, so we have 2 cosine theta plus sine 2 theta. Let's take that derivative. Yeehaw. We're going to get negative 2 sine theta. And what is the chain rule derivative of sine 2 theta?
Cosine times 2 theta times 2.
Good. So you'll have 2 cosine 2 theta, right?
Yeah, exactly. Yeah, my bad.
Okay. No, you're good. You had it. I just put the 2 in front. Okay. So now we want to set this equal to 0, but not yet. Because if we do, we're going to have to figure something out with these trig functions, which means we want to simplify this more. So does anybody have or remember the identities for cosine 2 theta?
Yeah, divided by 2.
In a moment, sir. Anybody know an identity for cosine 2 theta that would put this equation all in terms of sine? I'll Venmo you $1.
1 minus 2. No, wait. 1 minus 2 sine squared theta?
Yeah.
You looked it up.
I sure as shit did. I have all my notes right here.
Good. That's what they're supposed to do. If you're on your computer, just Google it.
Oh, well, that felt like cheating. I don't know.
All right. All right. Well, I figured everybody on the computer or phone, so just type it in, but like double angle for cosine. All right. But you got it. You looked at your notes. Good. That is good. Okay. So now this puts this all in terms of sine. Negative 2 sine theta plus 2 minus 4 sine squared theta. Marvelous. So now let's go ahead and set this equal to 0. And I'll write it, of course, with the highest power first. So -4 sine squared theta minus 2 sine theta plus 2 equal to 0. And like Ryan said, we can divide everything by what?
2.
But by
2.
2.
You can divide everything by -2 at that, right? Which would make
Don't get ahead of yourself, sir.
Oh, sorry. You'd get positive 2 sine squared theta plus sine theta minus 1 equal to 0. If you divided everything by -2.
So you don't want to just factor out a 2? It's
I-
same
It's
thing,
the
right?
same thing because you'll eventually end up dividing it anyways. That's what's awesome about an equation. You can factor it out and then divide it, or just divide it from everything. Does not matter, right? Okay, so now you have 2 sine squared theta plus sine minus 1. What can we do here?
Factor out a sine theta.
Can't factor out a
Oh,
sine
just kidding.
because
There's
of
that
that.
-1. I knew
right?
that.
Add the 1 on the other right side.
You can do that too, but you
It
make our
almost looks
life
like
a little
it's a quadratic.
difficult. What if I wrote it as 2x squared plus x minus 1 equal to 0?
Probably factor that.
There you go. It's the same exact thing. So I'll leave that there. What is this factor to?
Can hear them typing away on.
Now they're Googling,
Wolfram.
what is this factor to? Well, lucky for us, what are the only factors of 2?
2
1
and 1.
and 2.
1 and 2. And then again, lucky for us, what are the only factors of 1?
1.
It's a trick question, right? 1 and 1. You just have to make your signs appropriate. Where's the plus and minus go?
Minus in the first parentheses, plus in the second.
Now just replace those x's with what?
Sine theta.
Sine theta. Oh, right. Well, I guess we can do that after we solve for x. Why not, right? Let's call this the subline. All right. So then if you solve these, you'll get x equals 1/2 and x equals -1. But what is x again?
Sine theta.
There we go. Okay, everybody good with that? Now, on your unit circle, what radian values make sine 1/2? Oh boy.
Starts with a pi.
Pi over 6.
Pi over 6. Good. And where else?
5 pi over 6.
5 pi over 6. And then, where is sine equal to -1? Eh, you were close, dude.
3 pi over 2.
3 pi over 2. Here's our critical numbers. Woo! But again, we're looking for absolute maximums and minimums. So we need to make sure they fit in 0 pi over 2. So what are the only radian values to fit in 0 to pi over 2?
Pi over 6.
Pi over 6. That's the only one we can use. My goodness. So x and y. And there's 0, there's pi over 6, there's pi over 2. and you plug them into the original function, right? Desmos. Let's see, let's just use x. 2 cosine x plus sine 2x, close. And since you're plugging in radian values, make sure your calculator is in
Radians.
radians, which I think Desmos always starts off in radians. So then use my table, and then 0, and then pi over 6, and then pi over 2. All right. Two, 2.598, so 2.6, and 0. All right. Where's my absolute minimum?
0.
Where's my absolute max?
2.6.
There we go, y'all. That's it, right? Done. That's how you find critical numbers and absolute maximums and absolute minimums. I believe next class, we're going to take critical numbers, and then we're going to find local max and minimums by creating sign charts and a bunch of fun stuff. So that's it. We are done.